I don't know, I guess it's a tablet technically. So we'll see how this goes, but hopefully this will look a little bit more like a typical board work kind of pace and interaction with you guys, and hoping that will smooth things out a little bit, just in the sense that I can probably move too fast, clicking in a bunch of stuff that comes in from what do they call them, animations in PowerPoint, and that can probably be challenging. So today, what we're going to do is go over pressure distribution, and this is on our way to eventually talking about how manometers work, which we'll start tomorrow in class, and then we'll start talking about curved surfaces and so forth. So a couple of things, I have 4 or 5 problems lined up. We'll go through them through about 5 p.m. today here in Mountain Time. Note one thing that I overlooked somehow. On homework 3, you have one problem that's essentially repeated in parts one being the Wiley problems, remember, and then part 3, which is the paper problems, parts 2 and 3 of the paper problems. That was totally inadvertent. I apologize for that. You'll probably have different numbers for both, is my guess, but there may not. It's kind of luck of the draw. But I'm not going to change this at all. We'll go ahead and grade both of them. So, and I'll be looking out for that a little more carefully in the future. So my apologies for that. If you've gotten to those 2 parts, or if you haven't yet, just note that's not an error. That is, well, it's an error on my part, but it's not something we're going to change before you guys have to turn this in on Thursday. All right. Let me see. Any questions before we get going? Okay, terrific. Just for, let's see if I have to, oh, whoops. Sorry, this is a little bit clumsy here. All right, I'm just gonna mute everyone except me until I think you all will be able to unmute yourselves, but click in the chat if you can't. Okay. Let's see, just need to move this. All right, great. Okay, so let's go over a couple of basics real quick before we get into the problems. Here I'm showing a really simple diagram of a fairly simple system, but you probably look at it and think, well, this looks a little bit strange in the context of what we looked at on Thursday was a vertical wall, remember? And this one clearly is at an angle. I just want to recall a couple of things that we talked about. Remember that the first thing we said is that, oops, let me go into pen mode. Oh, come on. Why isn't this coming up? There it is. Okay. So we said that del P del X is equal to 0, and so is del P del Y. In other words, pressure variation in the horizontal directions, both X and Y, are equal to, that's weird. I don't know why that happened. That should be a 0. And the only direction in which pressure changes is in the Z direction, right? So del P del Z is not equal to 0. In fact, it's equal to a minus gamma. Oh, this is annoying. Let's see here. Should be a minus gamma. One thing I figured out so far is that I cannot erase. So I'll just try to draw slowly, I guess. So minus gamma. Remember, gamma is our specific weight. So it depends on the specific weight of the liquid under which, or the gas that we're in to calculate this value. Now, you can see I've let point number 1 come in here, and I'm going to put in point number 2. These are just 2 elevations, okay? Eventually, we will get to talking about the pressure distribution on this gate or this hinge, and P, that force, whatever. But for now, let's just talk about these 2 elevations, because even if the 2 locations we cared about were point number 2 being here and point number 1 being here, the only thing that matters is the fact that they are 2 different depths below the free surface, right? The free surface is up here, okay? So we also said that P1, remember that's the deeper location, is equal to P2. Oh, come on now. Yep, that's not going to work. Okay, P2. Oh, Serenity now. Okay, P2. And then we're going to add gamma times H. And in this case, H is going to be this distance right here, the elevation difference between point 1 and point 2. So these pressures, the pressure that you would calculate at either the point that I've drawn here or the hinge are going to be identical because those are both the same distance below this free surface. Same thing at point number 1, whether it's this location or this location at the bottom of this gate, both of those are going to have the same pressure, all right? And their elevations are different by H for both of those locations, whether we're talking about the hinge is H higher than the gate in elevation, 1 is H lower than 2 as well, all right? Now, we can rearrange this a little bit, of course, and say simply that P1 minus P2 is equal to gamma times H. So in other words, that the pressure difference between these two, of course, is equal to gamma times H as well. All right, so all we've done is rearranged this relationship. All right, the other thing that maybe I could have started with, but I'll just reiterate here, is that P1 minus P2, so the difference in pressures at these two elevations is equal to gamma times the difference between the elevations, Z1, Z2, I forget, 2 is above that, Z2 minus Z1, okay? So we've called this H, but the other thing to just reinforce with this equation is simply that when you change Z, you change P, all right? And those changes are proportional or translated by our gamma value, our specific weight, all right? All right. Okay, so let's go through some problems here. This one will start out fairly simple and sort of build in complexity. The question here is, what pressure expressed in pascals? So just recall real quickly, a pascal is a Newton per meter squared, right? So force per area. So what is the pressure? What pressure will a skin diver be subjected to at a depth of 50 meters in seawater? Okay, so the simple relationship here is P is equal to, in this case, gamma times H, okay, where H is the depth of the water that we expect to have. Now, I'm going to add this plus P naught, all right? And this question, we're not given any information about the atmospheric pressure at the surface, that sort of thing. So we interpret this, we assume that P naught is equal to 0, and that we're really looking for a pressure that is different from what the skin diver would experience at the surface, like before they jumped off the boat to go into the water, all right? So we're going to assume that P0 is equal to the value of 0, all right? So if this goes to 0, then we have a very simple relationship here, right? The pressure at 50 meters is equal to, now we're going to have, I'm going to just write this in and we'll look it up here in a second. The specific weight of seawater, so I'm just going to call that SW. Oh, really? I mean that to be a W. Ugh, that looks terrible. Sorry, folks. SW times H, the depth that we are below the water surface. So if I go to table 1.6 in your ebook, then you'll see that the specific weight of seawater is equal to 10.1 times 10 to the third newtons per meter cubed. Okay, and you should be expecting with specific weight a force per volume, right? So that works out. Okay, that's what we would expect. All right, so let's put that now into our equation here, and we would end up with 10.1 times 10 to the third newtons per meter cubed, and then times 50 meters. 50 meters. When we work that out, we come out to 505 newtons. Oh, sorry, times 10 to the third. Sorry. Wait, I think I've... Yeah, that's right. Yeah, 505 times 10 to the third newtons per meter squared, which is also equal to 500, oh, goodness sakes, 505 times 10 to the third pascals. Okay? So that is our answer, and that should work. Now, there's one thing that we could do to just make this a little simpler. The first thing is to say that, well, if we express this in kilopascals, we could get rid of that 10 to the third, right? Kilo of anything is 10 to the third, right? So we could say that this is 505 kilopascals. Now, sometimes, are we still answering the question the way it's been asked because it was asked to be expressed in pascals? Yes, as long as the point here is that you're not changing to pounds per square foot or pounds per square inch, something like that. All right, so we'll keep the kilopascals there. The other question, though, that I have is what about significant figures? You'll note that in let's see, let me change colors here real quick. Go to blue. Okay, so this number that we were given has three significant figures, right? We have the 1 and the 0 are important because, or both of them are significant because we have that 1 on the right side of the decimal place. So three significant figures there, but this number only has one significant figure, right? The 5. And so if we were working through with significant figures, this should really be 500 times 10 to the third. I'm just going to skip the one step and just say for significant figures, this would just be 500 kilopascals. Okay. Remember that significant figures, if you read through the recommendation, the overview at the back of your textbook, the one thing that's important about this is simply that you need to go with sort of the grossest of these numbers that are provided, the ones that are sort of the least precise, essentially. And so our significant figures help us with that. All right.
I have a question about that.
Yep.
On exams, on exams, will we be docked points if our answer doesn't do that? Like if this had been a question on an exam and we had said 505 and it was supposed to be 500, if it didn't specify, make sure you have the specific, the right number of sig figs, would we get points taken off?
Yeah. So from here on out, so that was my message. I can't remember if it was Tuesday or Thursday of last week, but that from here going forward, we're going to start applying significant figures. So you'll need to make sure that you've got significant figures in all of your work moving forward. So yes. And off the top of my head, I guess I'm not quite sure. Within a rubric, we would tell you, it was 2 points because, or 1 point or whatever. because you didn't have significant figures. So that'll start to be included, and that's really important in this case because when you start to get into hydraulics in particular, you'll have to start to apply that. So we're trying to get you into good practice now. Real quick, I see some questions in the chat. Oh, sorry. I guess I should just go back. Is that enough to satisfy your question there? Sorry, I missed who said that.
Yeah, thank you.
Okay, perfect. Real quick, so there's some questions about P atmosphere and so forth. The H was equal to 50. The question about P atmosphere, we're going to get to that starting tomorrow. So for right now, everything has been kind of idealized such that we're not worried about atmospheric pressure at the moment, but we'll start talking about where that comes into play tomorrow. I think 50 is an integer. In this case, though, if it's not followed by a decimal point, it's only considered one significant figure. Where's another question? I was asking for gauge pressure. Yeah, we'll get into gauge pressures and absolutes tomorrow in class, so we'll just hold off on that for the moment. Though 500 is 500 times 10 to the third. We have not, let's see, I have not put a decimal place anywhere in there. I grouped by convenience, so it should only be one significant figure, I believe. Okay, all right, so let me go on to the next one.
Real quick, didn't you
Yep.
say that there was something in the textbook, like that we could just brush up on significant figures?
Yep, it's in section M or something. It's like at the end. If you look actually in the way it's presented online, the text, it's at the beginning. It's called like, I think mathematical overview or something like that. And so there's like, there's some other reviews of like calculus and stuff, but one of the little sections in there is called an overview of significant figures. So there's two things. There's actually, there's text you can read, and then there's also a video.
Okay, thank you.
Sure.
Professor.
Yep.
So you don't need to account significant figures with like dimension changes, right?
Well, you do. You have to watch out if you have so if you're, what's the right word here? The conversion factor goes out to like 5 decimal places. Yeah, you do have to watch out, right? Like you don't want to. So if I just had, 1 foot, let's say I knew it was 1 foot, and I convert feet to something else, I need to stick with that 1 being the significant figure and not add 5 more just because I've used a value that had 5 more. Does that make sense?
Right. So if I said like 1 foot is 12 inches, my inches would have to be one significant figure.
That would come out to, I guess
Right?
it would come down to 10, wouldn't it? Yeah. in that
Because you'd
case.
start with 1 foot, so you'd
Yeah,
convert-
right.
Okay.
Right. Yeah.
Okay.
Now, if you were given 1.0 feet, but then you're okay because you're indicating that you're precise to that tenths place. Then
Right.
you-
But the conversion factor itself has nothing to do with your
right. Yeah. Yeah.
starting value. Okay.
Yeah. Good point. Good question.
Professor, I had a question.
Yep.
So when it comes to calculating, we don't use the significant figures until the end of the calculations, correct?
No, I was actually just trying to point out here that we worked through this, and then I wanted you to keep in mind the significant figure. So please do that throughout. This one was simple enough that it was easy for us to go back and just say, okay, if I had made sure that I used only one significant figure, this should have been 500, and we could work it through. So in general, though, you particularly because you're going to have more complex problems. Make sure that you're paying attention to significant figures as you go. So yeah, sorry, Mohammed, I didn't mean to throw you guys off. I do want you to do that as you go through. All right, terrific. Let's see if I can find my cursor here. There it is. All right, let's go to the next one. Okay. Sometimes when riding an elevator or driving up or down a hilly road, a person's ears pop. Hopefully you guys have experienced this and it wasn't too traumatic. As the pressure difference between the inside and the outside of the ear is equalized. Oh, I misspelled determine. Determine the pressure difference in PSI associated with this phenomenon if it occurs during a 150-foot elevation change. Okay, so as you can expect, our H here is now, Ay, ay, ay. All right. I haven't figured out the secret of this yet. I guess slow. H is equal to 150 feet. Okay. So that's going to be our H. Now, in this case, what we're looking at is essentially some change in pressure is equal to gamma times some change in elevation, right? We could call that a delta H. I've already called it H, so we'll use that. Now, this gamma we're actually going to use, remember the fluid that we are in is the air, okay? So if you go to look at, for these first couple of problems, I'm indicating the tables where you can find these in your book, in your ebook. So this is table 1 point, let's see, oops, wrong problem. Oh, table B3, which is a bunch of values for air at different temperatures. And I'm just going to assume at 70 degrees, oh, are you kidding me? That does not look like a 7. Let's try that again. 70 degrees Fahrenheit, I would find that this specific weight of air in my pounds force units here instead of newtons would be 7.49, oops, there we go, times 10 to the minus 2 pounds per foot cubed. Right, that makes sense. If we had a cubic foot of air, of course, we wouldn't expect it to have much of a force to it, much of weight. All right, so we can plug this in here on the right-hand side, and we end up with 7.49 times 10 to the minus 2. Oh, that's supposed to be a 0. 10 to the minus 2 pounds per foot cubed. Oh, what is stuff? Okay, and then multiply it by 150 feet, which is our change in elevation. We end up with a value that is 0.0778, but I have to be careful about that because, again, my sig figs will come in, right? I've got 3 here, but only 2 right here. So we get 0. I'm gonna write it out again. 0.0778. I'll figure out an eraser here at some point. 0.0778. Oh, whoops! I forgot to do my conversion here. Sorry, I jumped ahead. This was in that was in PSI. I forgot to do my conversion. So sorry, sorry, I jumped ahead a little bit. Wrong part of my notes here. So 1 foot square. So this is like we can work this out in feet. But when we do that, we're going to end up with a bit of a challenge in the sense that we don't have PSI, right? And we're asked specifically here for pounds per square inch instead of pounds per square foot. So recall that 1 foot squared is equal to 12 inches, which is what we have in a foot, squared, which is equal to 144. 144 inches squared, right? So now I can, so I'm going to end up with, let me see if this should come out to be 11 pounds per foot squared. And then I'm going to multiply that by my conversion here. 1 foot squared over 144 inches squared. And when I do that math, again, I keep my two significant figures. So delta P comes out to be 0.076 psi. Okay.
Professor.
Yep.
So I found that like when working on homework questions, kind of like this, it's like water at 59 degrees Celsius or the air pressure at 10,000 feet. I'm not exactly always sure like where to go in the textbook for the tables, and I find that's what slows me down a lot of the time.
Okay.
So like on exams, are these values going to be more specific, or are we going to be digging through tables on exams too?
Let me think about that for a second. What we're going to do on the exams is if we were doing this in person, what I'd like to do is just provide you with pages at the back that will be those tables that you could go right to, so you'd have them at hand. I think what I'll do for an online exam, because you guys are going to have to do it online, is provide you with just a separate PDF that you could keep open in one window while you're working on the exam. So that PDF would just have all these tables that you need. So you would have those constants right at hand.
Okay, thank you.
You bet. Okay, terrific.
I actually had a question.
Okay.
If I did like the whole entire conversion straight away without doing like 11 divided by 144, I got 0.078. Would that be wrong, or are you supposed to like convert the first thing first and then?
Yeah, so you have to acknowledge the significant figures where they're supposed to occur, because otherwise you may impart. I think what you did, for example, is a good example of imparting a little extra precision that wasn't there, and then you get thrown off when you do it later. So yeah.
Okay, cool. Thank you.
You bet.
Just to clarify, where you got your value from the table, that, for example, has 3 sig figs, and so you're saying at the end of each calculation apply significant figures instead of the actual conversion itself? Like 7.49 has 3 significant figures, for example.
Yeah, I guess I'm wondering. So I plugged that in over here. Oh, so yeah, you don't have to make this 2 significant figures. Is that what you're asking? Like, you wouldn't necessarily make that one right. You can in fact, it actually had 4 and I rounded to 3 because I was just like, this seems a little excessive. But now that I think about it, putting in 4 here would have been better for the math, but I still would have rounded to 2 when I get to whatever that calculation is, right?
Okay, thank you.
All right, terrific. Let me see.
Sorry, wait. So just to clarify, in this class, we like round to the correct sig figs as we go.
Yeah, correct.
Okay.
Yep. All right. Let's see. There's the cursor coming back. Okay. All right. So here's one that's an interesting one. So in a certain chemical plant, a closed tank contains ethyl alcohol to a depth of 50 feet, and then air at a pressure of 25 psi fills the gap at the top of the tank. So we don't really know how tall the tank is. All we know is that there's an air gap, and then there's 50, and that's at a pressure of 25 psi, and then there's 50 feet of ethyl alcohol. Okay, so let me just draw that real quick. So I'm going to assume it's round. It doesn't actually have to be, but we'll do this, and somewhere up here there is an interface. So I'll draw my little free surface, and this is air, and this is I'm just going to write EA since this writing is more challenging than I thought. EA is for ethyl alcohol. All right, and what we know is that this total height down to the bottom is the height of the ethyl alcohol is 50 feet. Okay. So the question is, determine the pressure of a closed valve attached to the tank 10 feet above its bottom. So here's, we can just draw a little like valve here and just say that this height is 10 feet above the bottom. And therefore it's 40 feet, right, by difference below the top surface, or the interface between the top of the ethyl alcohol and the air. So this is some H, and we know H is equal to 40 feet. Okay, so now, whereas with the previous questions, you guys have asked a good question about, well, what about the atmospheric pressure? In this case, it's not quite an atmospheric pressure, but it's a pressure at the top, right? So the pressure at 10 feet is going to be equal to whatever pressure, in this case, it's pressurized. So we have some pressure at, I'm going to put at 50 feet in elevation, okay? And then we're going to add the pressure that is added from the height of the water, the ethyl alcohol above this valve. So now we're going to have gamma ethyl alcohol, EA, times that H value, which in this case is 40 feet. Okay, so we are given that this pressure is 25 psi, right? That's what's filling in here. So this is equal to, oh, goodness sakes. All right, 20, that should be a 2, 25 psi plus, and then we need the specific weight of ethyl alcohol. So I've gone to look that up, and the value that I find in table 1.5 is EA is equal to 49.3 pounds per cubic foot. And the reason that I went with pounds per cubic foot is that we already had this all working in feet, right? I didn't convert to meters or newtons. By the way, this is at 68 degrees Fahrenheit. And because we're not given any other information about temperature, we can assume room temperature and be okay. All right, so now we're going to write in here. So we've got 49.3 pounds per foot cubed. And we're going to multiply by 40 feet. Sorry, this is getting a little bit squished. But now I'm going to take this one step further. I'm going to multiply out that second term. And I'm doing this to just kind of make a point. So this is 25 psi, pounds per square inch. Really? I made the S. It doesn't look like an S and an I. PSI. Plus, when I multiply this out on the right-hand side, I end up with let's see, 19. Well, this would come out to 1972 pounds per square foot, but I've only got one significant figure here for the 40, so I'm going to end up with 2,000 pounds per foot squared. Okay, now the reason that I did this is I just wanted to point out, you see that we have two different units, right? We have pounds per square foot and pounds per square inch. So what I need to do is convert that first one from 25 psi, we're going to multiply that by 144 inches squared per foot squared. And then we're going to add our 2,000. Come on. Now, I could have gone the other direction as well. I just decided to work in pounds per square foot instead. The question does not specify which units to use. All right, so this would come out to be on the left-hand side, this first term, this comes out to be 3,600 pounds per foot squared plus 2,000 pounds per foot squared. So this would come out to be 5,600 pounds per foot squared. Okay? So that's helpful, I think, in thinking a little bit about how to work these problems. If you were designing the that valve, you would have to make sure that you accounted not just for the 2,000 pounds per square foot that would come from the ethyl alcohol, but also that 25 psi, right? That ended up being, it turns out, a bigger total pressure when we got these into the same units than the ethyl alcohol by itself, which is interesting to note. All right. Okay. I think I had some blank space to work here and we didn't need it. So let's go ahead and jump to one of these problems here. I just need to hit escape. I think I have to end the show though. So let me keep that. And I got to pull up my reef. Come on. There it is. All right, so let me go ahead and start class. I'll bring the problem back over so you guys can see it here. Oh, man. All right, here it is. Okay, on any given day, does everybody know where Nederland is? If you're in Boulder at campus and you go up Canyon Drive and eventually start driving up the canyon, you'll end up following Boulder Creek on your left-hand side. You'll cross over it a couple times, and then you'll get to this little town of Nederland. Nederland is at, I think, about 8,000 feet, and Boulder is at just over 5,000 feet in elevation. So on a given day, the atmospheric pressure in Boulder is what compared to Nederland? So in other words, which one is greater? It would be expected to be greater in Nederland or in Boulder. So I'll give you a minute here to work that out. Hopefully you can see that. I think I'm still sharing that second screen. By the way, small victories. I was able to get the sync to work between the Reef app and Canvas. So that worked earlier today, only for the one period that we had last week on Thursday. So I need to get the other ones integrated. I'll do that prior or soon. And we'll probably just end up doing this once a week to get everything updated. All right, we're up to 81 responses. We'll give you guys a couple more seconds here. I'll give you 10 more seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. All right, let's take a look at it. So where should the atmospheric pressure be greater, Nederland or Boulder? 61 of you answered Boulder, and that turns out to be the correct answer. And the reason, remember, we talked about going when it comes to an atmosphere, the more atmosphere you have above your head, the higher the atmospheric pressure ought to be. Okay, so it would decrease as you went up in elevation, as you went up to Netherland. All right, I've got one more of these queued up. Let's look at. Sorry.
Wouldn't the pressure also go up based on the temperature? Like the colder it is, the higher the pressure would be.
Yeah, it sort of depends on what's going on with the weather. I tried to use, assuming that conditions were otherwise, it's the same air mass kind of over these two locations in general. We would expect that this should work out. We'll talk about atmospheric pressure tomorrow in class, but just because the temperature changes, you're talking about a full air column above you, kind of as far as the atmosphere goes. And so the little changes, right, where we see a lot of heating and cooling at the surface, are not the only thing that would impact that whole air column above us. So yeah, a good question, but that we expect that variability to be a little bit lower. It's pretty damped within a day until like a cold front comes through with low pressure behind it or high pressure sets in. Then we have bigger barometric pressure changes. Okay, so let's reset here. Let's see, I think I need to do this and then start a new one here. Okay, so now I didn't jump to the next question, sorry. All right, here we go. So if the depth of a swimming pool is 4 meters, then compared to the pressure at the surface, the pressure at the bottom is the same as that at 2 meters, half that at 2 meters, twice that at 2 meters, or triple what we have at 2 meters. All right, so this is really just about how does pressure compare. Let me get this going. I'll give you guys a minute. So A, B, C, or D, same as the pressure at 2 meters, half that at 2 meters, twice, or triple, 3 times. All right, 78 responses. Let's see what we get here. All right, let's give it 5 seconds. 3, 2, 1. All right. There we go. Okay, so let's take a look at the responses here. All right, we have most responses for C. So let me read out C. If the depth of the swimming pool is 4 meters, then compared to the pressure at the surface, the pressure at the bottom is twice that at 2 meters, and that is the right answer. What I was trying to do is get you guys to think, not worry about the atmospheric pressure or whatever that's occurring at the surface, but relative to that, how does this change? And it's a linear change, so we assume it's a swimming pool, so it's water, but there are a lot of saltwater swimming pools now, right? So we don't know the exact specific gravity or specific weight rather, but regardless of that, you should have a linear change, which means that you would double the pressure of the overlying fluid as you doubled the depth, right? So that should work out. Okay, terrific. Let's see. Okay, so let's go ahead and cancel that now. And we will end class for that period. Okay, get back into this. I've got one more question lined up here. And it goes through, it's kind of a good transition to tomorrow. So let me just real quick say, I'm going to work through all this. The recording is going to be online. If anybody has to leave right at 5, feel free to do so. And you can catch up with this after I post the video later tonight. All right. Real quick. So blood pressure is commonly measured with a cuff placed around the arm. The cuff pressure, which is a measure of the arterial blood pressure, it will be indicated with a manometer. The typical value for the maximum value of blood pressure, what we call the systolic pressure, is 120 millimeters of mercury. Why wouldn't it be simpler and less expensive to use water in the manometer rather than mercury? Mercury is kind of a nasty material. If you've ever had to deal with it before, it's not something you want to touch. So there is some danger with mercury. Why not just use water? All right, well, the question really comes down to a question about whether we can, there's some advantage to using mercury. All right, so let's take a look at this video real fast. Let's see if I can get it queued up. Oh, shoot. I've got too many different windows open here. So here's our cuff on the outside of someone's arm. Hopefully all of you have experienced this before. We pump up that pressure inside the cuff, and we watch for sort of it to decline and get in rhythm essentially with the pressure that we have in our veins and blood vessels. All right. So 120 is about the highest that we expect to see. So the question, so that becomes an important clue for us to be able to move on in thinking about how this is going to work. So get my pen here. All right. So remember that the column that we're talking about here is a column of mercury, and it's inside of that tube that we saw on the right-hand side of that video. So we're not talking about a column of blood, and we're not talking about the specific weight of air. We're really talking about the specific weight of mercury, because that's what is being pushed up by the pressure that is our blood pressure. So if I look this value up, by the way, I get 133. Oh, rats. 33 times 10 to the third. And that is newtons per cubic meter. Rats. Newtons. That'll be my fraction now. It's supposed to be an N. Okay. Newtons per cubic meter. All right. So to hold that up, 120 20 millimeters of mercury. The question is, what pressure do we have? What actual blood pressure are we getting? Okay, and we can figure that out by basically writing the very simple equation: P is equal to gamma times H, right? Where there's some pressure that is pushing up this 120 millimeters of mercury. And so we can basically equilibrate this, really, okay, to being our blood pressure, P, is equal to gamma of mercury times whatever height of mercury is in what we call the manometer. Okay, so this blood pressure then would be equal to 133 times 10 to the third newtons. Oh, I got too fast. Newtons per meter cubed times, I'm going to go ahead and do this conversion because we need to go from millimeters, 120 millimeters to meters, right? We're going to have to work in meters. So if I just make this conversion 0.12 meters, or basically 12 centimeters, we will end up with the right units when we work this out. So I've got two significant figures on this measurement on the, I take that back. No, that's right. I do have two. On the right-hand side, after I've done the conversion. So I end up with 16 times 10 to the third newtons per meter squared, or 16 kilopascal. Okay, now that's the pressure that we're going to experience. The question that's being asked is, couldn't we do this with water instead? Like, why mess around with all this mercury? And ultimately, there are two things that don't change in this equation that we have on this equation right here, which is the pressure, right? And I guess there are two things that do change. The one thing is the pressure. Whatever pressure we are going to have we experience, when we measure it with mercury, we're going to have a certain height of mercury. When we measure it, if we measure it with water in the manometer instead, we'll have a different height of water to get the same pressure. Okay, so we're going to rearrange this equation and solve for the height of water given this pressure. All right, so now we have 16. So when I rewrite this equation, I'm going to end up with P, our blood pressure, divided by, now we're going to have gamma water instead of mercury. And so we end up with 16 times 10 to the third newtons per meter squared, divided by my value for water, I'm going to take to be 9.8 times 10 to the third newtons per meter cubed. All right, now I kind of threw that in because I knew that 9,810 is the specific weight of water. And so I just went ahead and converted that to 10 to the third units, right, instead of, or 10 to the third groupings instead of putting it in kilonewtons. And so when I work this out, then I get a value of 1.6 meters. Okay, so if we were to use water, our manometer would, instead of having to be several centimeters, well, I guess, what is it, 12, that was 12 centimeters. If maybe being, I don't know, 20 or so centimeters, I don't know how much we'd expect on the high end, but certainly it would have to be a little bit bigger than 12 centimeters or 120 millimeters. Now I would need 1.6 meters of height if I used water instead. And so the point that I want to make here is that it really comes down to this difference in the specific weights. The specific weight of mercury is much larger than is much bigger than the specific weight of water, right? And it is 133 times 10 to the minus third versus 98 or 9.8 times 10 to the third, right? So it's like more than 10 times greater. All right. On the next slide, I just wanted you to note that I've seen this comparison before in one of the previous versions of this book, but essentially, a meter of mercury in height is shorter than, kind of your average adult, but the water equivalent of that then is more than 10 times that height, right? And that's the point that we just want to make here. Note that the ratio here, by the way, the ratio of these specific weights is 133, oops, I forgot the other three, times 10 to the third newtons per meter, jeez Louise, cubed, divided by 9.80 times 10 to the third newtons per meter cubed. And so that comes out to 13.6. Ugh. It's supposed to be a decimal point. So that should be 13.6. All right. I need to write patiently, I guess. All right. So there we go. And that's why mercury we're going to find in a lot of manometers in the problems that we're going to work tomorrow and into the future in the next homework, because the higher density and the higher specific weight means that you can kind of compact your range of heights that you need for measuring pressures. Okay. All right. Why don't we go ahead and end there, since how are we doing on time? We are just a few minutes past 5, so apologies for going over. But as I said, whenever we go over, if you need to leave at 5, that's fine. I can post the video afterwards. Any questions? I think I'm going to stop sharing here so I can see faces. And I'll be happy to post this, and it'll be available for everyone.